There we go. I think you should be able to see my screen.
Yeah, it's okay.
Okay, and the pointer as well.
Yeah, it's okay.
Right. Right. Okay. So.
Okay, then the last speaker of this morning section is Dr. Nils A. Nilsson from Shikest. The title of the talk is Primordial Gravitational Waves in Space-Time-Symmetry, Breaking Gravity. Okay.
So thanks to the organizers for organizing this workshop. I realized that my title is a little bit misleading. As I was putting together this talk, it became less focused on primordial gravitational waves and more focused on cosmology in space-time symmetry, breaking gravity in general. So in cosmology, we've heard several talks in this conference how there's trouble in cosmology. And we have kind of a puzzle piecing together what the geometry and evolution and history of the universe is. And in standard cosmology, we heard about the horizon problem, we heard about the flatness problem, we heard about the H0 tension, and inflation can solve some of these. And there are many models and approaches to reducing the H0 tension and the SA tension as well, which is related. But then there's some open questions, like we don't know what dark matter is, we don't know what dark energy is. We're not even sure about the geometry of the universe. Is it flat or is it not flat? So I think every day there are new papers coming out, either trying to reduce the Hubble tension or trying to explore some aspect of dark energy. And one of these approaches is to break some symmetries. And so you can add, for example, parity violating terms. You can break Lorentz symmetry. You can break CPT symmetry. And you can see what happens to cosmology. And this is more or less what I do. So I show this Lego depiction of the universe in almost every single talk I give. So there's a lot of phenomenology in breaking space-time symmetries because Lorentz symmetry is right here, and it underpins everything. Basically, all of everything we know about fundamental physics is based on Lorentz symmetry. So even if the universe is perfectly Lorentz invariant and Lorentz symmetric, it's still worthwhile, I think, to test such a fundamental assumption to a high accuracy, because otherwise we simply don't know. And it's an assumption that I think should be tested. Because if Lorentz symmetry is some effective field theory, then there's a cutoff scale. And if you go beyond that cutoff scale, maybe the Planck scale or some gut scale, then you can't be sure that your results are Lorentz invariant. So I use a standard effective field theory for studying space-time symmetries. And there are papers from started appearing in the early 1990s, I think even 1989, by Alan Kosteletsky and his collaborators. And it's built in such a way that you have conventional physics, so the standard model, general relativity, and then you have a series expansion, which contains every single possible operator which breaks Lorentz and or CPT symmetry. And it's built kind of like this. You have some coefficient, which are called the coefficients of Lorentz violation, you can call they're all Lorentz contracted into some conventional field operator, like the Ricci tensor, in the gravity case, of course. So normally what people do in the exact, when studying these things exactly, is that you truncate this series expansion at mass dimension 4. And that means you only have one term. It's this term, contracted with the Riemann tensor. And this tells you all that you can know about any departures from exact symmetry that's encoded in these coefficients. And then you manipulate these expressions in various ways, and you constrain these undetermined coefficients with experiment. So this term is just it's called the minimal formulation. But if you can expand the series up to, let's say, dimension 6, and just to show you what it looks like, then you get something like this. So GR is here. This is the minimal extension, and so on and so on. And you can see that, at 6th order, you have quite a lot of. This term has 210 independent degrees of freedom. And then if you want spontaneous symmetry breaking, which in general you need in gravity, then you also have these kinetic terms and potential terms. And there's been quite a lot of work done on all of this. There is a paper which it's on arXiv, which get updated every year with all the current constraints on these coefficients, and it is currently, I think, 125 pages long, and it's just one long table. And basically, so if you have a favorite model of, let's say, Lorentz breaking gravity, it is already, this is a subset of this effective field theory, and any coefficients of that theory can be mapped onto these coefficients, and chances are there's already a constraint.
Absolutely. I have a question. So
yeah.
Is the K4, K5, all of them are functions or constants?
In general, they are functions of the space-time coordinates. But you can, of course, simplify it by saying that they're constants. And this is normally what's done if you do weak gravity. You expand around some constant background, and that makes things a lot easier. So I'm more or less only interested in explicit symmetry breaking right now, and only, my mouse is not working properly, and only this term. So what you do normally is that you decompose this into scalar, traceful, and traceless, and you get these 3 terms: the Weil tensor, the trace-free Ricci tensor, and the Ricci scalar. Now, there's a puzzle in this effective field theory called the T puzzle, because if you do parameterized post-Newtonian expansions, this term is 0 at all orders, and we're not quite sure why. So what I'm going to show you in these the rest of the slides is focused on this term only. So it's a very, very simple model, a very simple case of explicit space-time symmetry breaking. So I take this S term, and I say that there's only one non-zero component. So this is really a very simple case, and this is what we started with, and we did the Hamiltonian formulation and the constraint analysis. And what we found more or less here is that there's an extra primary constraint directly proportional to the space-time symmetry breaking term. And you get, in general, you get 2 extra dynamical degrees of freedom out of this through the Dirac-Hamiltonian prescription. And at the background level, the cosmological equations look like this, where you have these 2 extra terms. Okay. And here we have some time dependence still left in the S00. So there's a coupling here between the acceleration equation, just as normal, together with the first Friedmann equation. And then actually it turns out that you get a modified continuity equation out of this. Because what you want to do, here you have to choose. So I choose to say that matter is not covariantly conserved on its own, but rather the full stress energy tensor is conserved. And what you get out of this is a modified continuity equation for matter, of course, which actually behaves as dynamical dark energy, turns out. So here you have, it's been rewritten as the standard Friedmann equation, but radiation, let me change color. See that radiation and the cosmological constant have some strange evolution here. And if you expand these, these terms, it turns out that everything behaves as FLRW, which is this term, plus some dynamical terms. Okay. And if we set this S00 to some ridiculously large value to see the effect of this de facto dynamical dark energy, you see that the scale factor evolves in this way, where this dashed line is some very, very large negative value of S00. So you have a higher scale factor in the early universe and in the late universe. And of course, just by boundary conditions, we coincide with the GR case today. So in the early universe, it's not really been studied using this effective field theory, but we have observables such as B modes in the CMB and the primordial gravitational wave background. Now, when you talk about B modes, you have to be careful because weak lensing at low multipoles can also give B modes in the CMB. It's not only tensor perturbations. But in some early work, there have been studies of inflation, for example, with spontaneous spacetime-symmetry breaking. And just from the non-detection of B modes, there's a constraint of 10 to the minus 43 on this coefficient T that I mentioned before that vanishes in ppn. And there was a very recent paper by this group in Brazil where they study, they classify solutions in symmetry breaking gravity for accelerated expansion to see which kind of solutions permit inflation at all. So this is well worth having a look at. Now, in some specific models, like Rojava gravity, a few years ago, there was a PRL paper. Let's see, there was a PRL paper about chiral primordial gravitational waves. Because normally in Rojava there's a cotton tensor term, and you get parity violation. So the degree of circular polarization is determined in this paper by this quantity, and you can see that these solutions for the Fourier modes are different from the right and left-handed chirality. So this is for just some values, chosen values of the model parameters in this approach to Rojava. And you can see that you can get quite a lot of circular polarization for large values of the model parameters. And if I remember correctly, in this paper, they claim that anything bigger, so on the right-hand side of my green line, it would actually be detectable in the future. So if I want to do some primordial fluctuations in my simple case of spacetime-symmetry breaking, let's say I choose this S00 to be a constant. I say that there is some coordinate system in which partial derivatives of this S mu nu vanish. And And it turns out that the action, which I'm then interested in, looks like this. So this is, again, this is general relativity. This is the 3D Ricci scalar. Alpha is the lapse function. Gamma is the spatial metric. And this is the acceleration, the ADM acceleration term. And if I then do some perturbations just around flat lambda CDM, I get a quadratic action which looks like this. And not much has changed, except that there's a constant scaling proportional to this S00 in the double time derivative. Now, what happens here when you do this is that you obviously, your equations of motions will change, and they change with this function theta that I defined. And theta is very, very close to 1. Let me emphasize that any non-zero S00 will be very tiny, and I get some constraints on it on the next slide. So, for example, if you want to solve this in the radiation domination era, you have to solve this equation, or you have to determine this theta, which you normally have to do numerically. Now, because of this modified continuity equation that I mentioned before, there's no pure de Sitter, which is why I have quotation marks around de Sitter. It's de Sitter plus a small tweak, which you can probably just reabsorb in omega lambda. But anyway, technically there's no pure de Sitter. So if you just want to solve this in radiation domination, in my quasi de Sitter, I solve numerically for these the evolution of the tensor perturbations, and just to see what's going on, and for some values of this S00, and you can see that the evolution is quite different in very, very early times. So this is k times eta, so which is negative during inflation, or in the de Sitter phase, and becomes 0 at the start of radiation domination. But this doesn't tell me much. It doesn't give me any constraints on an S00. So what I can do is I can go to radiation domination. So I solve my equations from here. And I get something curious, which I don't quite understand. But so because of just the structure of these equations, you can't absorb the comoving wave number by this convenient k eta, the standard k eta coordinate transformation. So I have to choose some values of k. So naively, I chose k equals 1, and I tried to solve these equations. And it turns out that with k equals 1, if you set S00 to anything larger than the CMB temperature times 10 to the minus 9, these equations can't be solved by standard numerical solvers in Mathematica, at least not on my processor architecture. So there's some problems, some singularities in the equations which become too large to handle if S00 is too large. Now I expect S00 to be very small anyway, and in fact I expect it to be much smaller than 10 to the minus 9. But this is like a numerical constraint. I don't have any data here. So just from the equations of motion, we can read off things like the speed of tensor modes. Okay, and it turns out that the speed of tensor mode squared is just this function theta, which I defined earlier, and just from we know from this the electromagnetic counterparts which were observed a few years ago that this tensor modes speed of tensor modes are very, very close to the speed of light. And here I can find some extra constraint on S00s on the order of 10 to the minus 10. And just before I run out of time, you can also say that this actually this implies a running of the Planck mass on the order of S00. So there's a lot of strange phenomenology in this model, and I want to emphasize that it's a toy model. I don't expect this to be physical, but some generalization of this might be. And I think I'm out of time, so I'll stop there.
So your mic it was turned on.
Okay, thank you for the speaker and the question.
Sorry, I have a question. So,
Yep.
so will you go to your ADM decomposed action with the S00?
Yes, I have it somewhere.
No, I mean, so you show some R plus kinetic term plus S0.
Oh, sorry, this one.
Yeah, this one, yeah.
Yeah.
Right, so here, the strange thing is that you cannot consider S00 equal to 0 in it. It is singular. What do you think about it?
Right. Yeah, it looks singular, but actually in the I don't remember now exactly how you, but that it shows up inside the acceleration as well.
So you mean that the AI is a derivative of Labs function, right?
Yes, it is. But there's an extra effect that comes from S00, which I don't exactly remember.
So you mean that you are saying that this last term is still regular in the
It's regular, yes. And the same thing, you can see the same thing actually from the Hamiltonian analysis. There are lots of terms that appear singular in S00, but they're not.
Okay, thank you.
And other question?
Let me see. So Alvin, your numerics are very interesting.
Yeah, I know. It's very strange.
Right. Can you get at this analytically? What can you do? I mean, you would like to see that those singularities are there.
That's right.
And I mean, how do you know this is the CMB temperature as well, right?
Anyway, I expect that this is a pure coincidence.
Okay.
Because you see that it's a function of this K, right? So
right.
I chose K naively to be 1. I thought I'll start with 1, and it just happened to coincide with the with 2.7255. But then, yeah, that's it. That's a pure coincidence, I expect.
Right, but it's probably worth looking at this analytically if you can. I don't know how you do that, but I mean, can you go to your equation, or what equations are you solving?
Essentially, I'm solving these. Yeah, but yeah, you don't want to study this analytically. I can tell you. But surely you can probably simplify it somehow. I expect that the problem is in this equation, but these solutions for the A's are not nice, let's say.
Right. Okay.
But yeah, there's some more now, and I'm doing it actually. I want to see where this comes from.
Okay. Thanks.
Yeah.
Thank you. Any other question?
Can I ask one more question? Okay, can I?
Yes.
Okay. Will you go back to the action?
Sorry.
Yeah,
there we go.
Yeah, this one. Yeah, so we can discuss later, but basically I am quite doubt about this, last term. because there is no time derivative in the last term. So it does not affect any Hamiltonian, the procedure. So if there is a singularity in the last term, it should also appear in the Hamiltonian. So anyway, the question is that here there is a additional scalar graviton mode always because of the last term.
Yes, we have an extra.
Right. Have you thought about that the scalar perturbation other than
here?
the
I'm only looking at tensor perturbations.
Right, but I think scalar perturbation is also important.
Yes, for sure.
Right. Okay, yeah, that's one question. Okay,
Yeah.
thank you.
Thank you. And the other question? If not, let's thank speaker again. And also let's thank all